In the previous video, we discussed the ionization of weak acids. In this one, we are going to be talking about um, the uh, the steps which are given at the end of your ionizations of weak acid. We were given like a step-by-step situation, and I thought, we're not going to be talking just about those steps because eh, that's boring. So what we're going to do is instead we're going to be solving this particular problem, and we're going to have the steps on the side, and then we're going to talk about it as we go. First of all, let's talk about this question. It's big, right? I know. So the ionization constant of HF is 3.2 into 10 to the power minus 4. So let's write that down. Ka equals to 3.2 into 10 to the power minus 4. Calculate the degree of dissociation of HF in its 0.02 molar solution. So we have been given the initial concentration of HF equals to 0.02 molar, and we need to calculate the degree of dissociation of HF, which means we need to find the value of alpha, like its degree of dissociation during the after it's basically reached equilibrium, right? So we have to also, not just that, calculate the concentration of all the species present. So we need to figure out the concentration of H3O plus, F minus, and HF in the solution, and we need to calculate the pH. Okay, so these are the things we need to figure out. So first of all, according to the steps given, we need to figure out for if the species present before dissociation are identified as Bronsted-Lowry acids or bases. So we know what Bronsted-Lowry acids or bases are. If you don't, definitely check out my previous video because that's super helpful. But basically here we know HF is an acid. Okay. The next thing we need to find is we're going to be writing the balanced equations for all possible reactions. So, so you have two reactions which are possible. First of all is going to be HF plus H2O gives rise to, or is an equilibrium with, H3O plus F minus. The second one is H2O plus H2O is in equilibrium with H3O plus OH minus. So Kw over here equals to 10 to the power minus 14. Ka equals to 3.2 into 10 to the power minus 4. Okay, so obviously the reaction with the higher Ka is identified as the primary, while the other one is the subsidiary reaction. So between these two, the value of Ka is obviously high, which means that's going to be the primary reaction. So this is the primary reaction. Oh no. Thankfully, we have a undo button because I'm using my computer. So this is the primary reaction, right? So this is the subsidiary. So we are going to be dealing with the primary reaction from this point forward. So that's step 2 and 3. Step 4 is enlist in a tabular form the following values of each of the species. So essentially we need to figure out we have to write down all of these in a tabular form. We need to have the initial concentration, the change in concentration on proceeding to equilibrium in terms of alpha, which is the degree of dissociation, and the equilibrium concentration. Okay, so let's first write down the equation again and go from there. Okay, so first of all, you have HF plus H2O is in equilibrium with H3O plus F minus. So the initial concentration, I'm just going to denote it by A, that is the initial concentration is obviously for the HF is going to be 0.02 molar. So this will be in molar, all the three. So 0.02, that's the initial concentration. You don't have anything for H3O plus and F minus. The next one is going to be B. We are considering the change in concentration on proceeding to equilibrium, and this is going to be in terms of alpha, okay, which is the degree of ionization. So we are assuming that it is decreasing by 0.02 alpha, okay, and this one H3O plus is increasing by 0.02 alpha, and F minus is also increasing by 0.02 alpha. So this is the change, okay, during the, when it's proceeding to equilibrium, this is decreasing by 0.02 alpha, which is alpha is the degree of dissociation, degree of ionization, I'm sorry. And then this is going to be increasing by that amount, right? Because this is breaking down to give us this and this. So C is going to be the equilibrium concentration, which is going to be 0.02 minus 0.02 alpha, and then this will be just 0.02 alpha, and this is 0.02 alpha. Okay, so this is it, right? So I'm just going to just simplify this a bit and just say 1 minus alpha into 0.02. This is somewhat similar to what we got when we were talking about the ionization of weak acids. Okay, so that's what we have. We have a tabular form of with the following given. Next thing is where it gets a little interesting. So we need to substitute the equilibrium concentrations into the equilibrium equation, constant equation for the principal reaction, and then we solve for alpha. So basically what this means is Ka for this equation is equal to concentration of H3O plus into concentration of F minus divided by concentration of HF. Okay, so we will substitute the values. So 0.02 in alpha into 0.02 alpha whole divided by 0.02 into 1 minus alpha. So this and this can get cancelled. And so we are left with Ka is equal to 0.02 alpha square divided by 1 minus alpha. Okay, now we know Ka has been given to us in the beginning of this question, right? Ka equals to 3.2 into 10 to the power minus 4. Okay, so this is, we'll have to solve for alpha. That's what we're going to do right now. So let's simplify this further. So 0.02 alpha square equals to 1, 1 minus alpha into 3.2 into 10 to the power minus 4. Now let's divide this whole equation with 0.02. The reason I'm doing that is to eliminate this guy. Okay, so I think that's what makes the most sense in my head, and that's how I'm solving this. If you have a better way or a different way that you do it, definitely let me know. I'll be really interested to know. So alpha square equals to 0.02 divided by 3.2 divided by 0.02 gives us 160 into 10 to the power minus 4 into 1 minus alpha. Okay, now we're going to simplify this a little bit more. Okay, so you have the decimal point here 1, 2, 3, and 4. So you'll be getting alpha square is equal to 0.016 into 1 minus alpha. Okay, so this further gives us alpha square minus is equal to 0.016 into 0. Oh, sorry, we're simplifying it. So it'll be giving us a negative sign minus 0.016 alpha. So let's simplify this further. Alpha square plus 0.016 alpha equals, minus 0.016 equals to 0. Now again, over here, it's up to you. If you want, you can like fast forward a bit, but basically we'll be solving this step by step. So first of all, you have the equation alpha will be equal to minus b plus minus root over b square minus 4ac whole divided by 2a. Okay, so here value of a equals to 1, value of b equals to 0.016, and value of c equals to minus 0.016. Okay, so this will be equal to, let's substitute those values, minus 0.016 root over 0.016 square, oh, plus minus, sorry, minus 4 into a into minus 0.016. This whole divided by 2a, which is 2 into 1, I'm just going to say 2. So you're going to be left with 0.016 plus minus root over 0.016 square is 0.000256 minus 4 in, so minus into minus is plus, and 4 into 0.016 is 0.064. So this whole divided by, oh, 2. Okay, now let's move over a little bit. I know. No, I did not mean for that to happen. Okay, so let's simplify this further. So you will be, when you simplify the inside of the square root, you get minus 0.016 plus minus root over 0.064256. Essentially, we're just adding them both, right? So we, so root over that number is 0 plus minus 0.2534. So this whole divided by 2. Now, obviously, the last step for us to solve a quadratic equation is to assume plus or minus. In this case, we're only going to assume plus because minus plus minus, I mean, when you have two negative values, you're going to be left with a negative value, and that means that, you know, the concentration cannot be negative. Because of that, we're not going to be considering the negative value altogether. So only be considering the positive value. So alpha will be equal to minus 0.016 plus 0.2534 whole divided by 2. Now this when we simplify, we get 0.1187. This is approximately equal to 0.12, which is simplifying it to get to 0.12. So this is the value of alpha. Okay, so we've figured out the value of alpha using the equilibrium concentration. Now we need to calculate the concentration of species from the principal reaction. Now if you remember, we wrote that the concentration of HF, no, let's start with the others first. So concentration of H plus or H3O plus equal to the concentration of F minus equal to 0.02 into alpha. Now we know the value of alpha is 1.2, 0.12, so 0. So we just have to multiply that with 0.02. That gives us the value 2.4, oh, 0.0024 molar. Okay, now because we are next we'll be calculating the pH, and it's easier to have it as a 10 to the power value, so we're just going to move this decimal point over by 3. So you're going to be left with 2.4 into 10 to the power minus 3 molar. The next one is the value for the hydrogen, the HF. So for the HF, it's going to, oh my goodness. Oh, okay, that was bad, but you know, It's fine. So for the HF concentration, HF will be equal to 1 minus alpha into 0.02, right? So 1 minus 0.12 into 0.02. So this, when simplified, will give us 0.88 into 0.02. And this is equal to 0.0176 molar. So this is the concentration of HF. So we figured out the concentration of the species. So that was the um, that was the sixth step, and the last step is calculating the pH. So pH will be equal to negative log concentration of H plus, right? So that is negative log 2.4 into 10 to the power minus 3. So this will be equal to minus log 2.4 plus log 10 to the power minus 3. So this is equal to minus log 2.4 is equal to 0.380. So 0.380 minus 3. And this, when simplified, gives us minus of minus 2.62, which is equal to 2.62. So the pH of the solution is 2.62. So essentially what we've done is we've used the various steps given to you in the step-by-step calculation for us to calculate the value of. First we figured out which was the primary reaction, and then we moved on to have a tabular form with the initial concentration, the change in concentration, and the equilibrium concentration. We then substituted in the value, the equation to Ka, and were able to calculate the value of alpha, and we calculated the concentration of species of the principal reaction from the value of alpha, and then we calculated the pH. Let me know if you would like me not to, do it step by step, or if you prefer it, and if you have a different way of doing this or solving this problem, definitely let me know. In the next video, we'll be discussing the next question, obviously, which is, my brain's tired. 6.19.